Welcome back to Akadimos Online. Let's think why the greenhouse gas molecules structurally retain permanent and instantaneous heat. How polarity of molecules are measured. It's the dipole moment that indicates separation of positive and negative charges within. All these are explained in today's class. It's derived from hybridization theory. Our guest teacher delivers qualitative idea of different dipole moment using vector formula to measure the direction and quantitative magnitude of molecules. So let's go ahead with our teacher Nurul Haque now.
Dear students, today I am to discuss an important part of fundamental chemistry, that is dipole moment. It is the part of chemical bonding chapter. From dipole moment measurement you will get idea about the polarity of the molecule and quantitative idea of polarization of electron cloud. I have discussed in oxidation number chapter that oxidation number will give idea about qualitative idea of polarization of electron. But here you will get quantitative idea of polarization of electron. And first part I will discuss about the bond moment. And from the bond moment, if you know the shape of the molecule or stereochemistry of the molecule, then you will get idea about the molecular moment. And so many properties like boiling point, like solubility with solvent, that will depend on this dipole moment of the molecule. You know, higher the dipole moment, higher the dielectric constant of the medium. That means so many molecular properties you will get from this fundamental idea, that is the dipole moment, and that will arise due to difference of electronegativity of atom in a bond. See that I am taking A bonded with B. Since A atom and B atoms are different, you know, if they are different, their nuclear charge must be different, their electronegativity different. That B is more electronegative. B is more electronegative than A. Then electron cloud will polarize from A towards the B, by which its formal charge not zero, it is not purely covalent. You will get del minus, that very little bit minus you will get, and this is corresponding del plus, overall is neutral, and the del is, you know, just to express the very small amount, and this is the quantitative figure, and that will depend on the difference of electronegativity. More difference of electronegativity, more is the value of charge separation. Now what is dipole moment? Actually dipole moment with respect to positive electric field. If I take a positive electric field here, what you will see, that you will get a moment. Actually the molecule will rotate around its own axis, that is bond axis, and its orientation will be the BA, this is delta minus and this is delta plus. Due to electrostatic reason, electrostatic attraction, it will rotate and by this way and oriented by this direction, and it will move towards the positively filled electric field. This moment, this rotation, this dipole moment, and that dipole moment will do expressed generally by mu, that is the charge separation into the bond length. You know from rotational dynamics, that is the bond length. Charge separation into bond length is the dipole moment, and from there you will get a quantitative idea about the charge separation or polarization of electron. Now you know, if I do express the charge separation in ESU and bond length in centimeter unit, that is CGS unit of dipole moment. That is the CGS unit of dipole moment, and a common unit of dipole moment, that is dY. Remember this dY is equal to 10 to the power minus 18 CGS unit ESU centimeter. That is the CGS unit of dipole moment. Another unit, generally we use SI unit or dY. That SI unit of dipole moment is, you know, charge is coulomb and meter. These are the unit of dipole moment, and quantitative measurement you will get here. And from this dipole moment measurement, you will get idea about the percentage of ionic character of a bond. That qualitative idea of percentage of ionic character You got in chemical bonding Fajans rule due to polarization of electron. Here you will get a quantitative idea of polarization of electron. How, that I am going to show you. General example, A bond B. Now this is delta minus, this is delta plus. Let here B is more electronegative than A. Now charge separation. This is charge separated delta, actual value of charge separation. Now if it will undergo complete dissociation, that is A plus and B minus, then we will treat as 100% ionic, 100% ionic. That means when the charge separation is E, charge of an electron, you know charge of 1 plus, magnitudically same. One is minus, another one is plus. So this is the fraction of charge separation. This is the fraction of charge separation. Fraction of charge separation. Fraction of charge separation. That fraction of charge separation will be expressed by delta, that originally charge separated due to difference of electronegativity, and if it will undergo complete dissociation, complete separation, then it is E. Now if I do multiply both denominator and numerator by bond length, this is the bond length, then you will get lambda delta into D, D is the bond length between A and B, E into D, E into D. Now this it will give the fraction of charge separation, and you can write this delta into D according to the definition of the dipole moment, that is mu observed, actual dipole moment of the bond, divided by E into D. Now this is the fraction of charge separation. This will express the fraction of charge separation. If dipole moment of a bond is given, for example HCl, dipole moment observed given, and E value you know, but remember unit should be the same, denominator, numerator unit should be the same. If it is in dBi, then this denominator also you have to take in dBi unit. If D I take 4.8 into 10 to the power minus 10 SU, and B generally given in angstrom, you know X angstrom, then it is X into 10 to the power minus 8 centimeter, and you will get the denominator in dBi, numerator also given in dBi. And if it is in coulomb meter, then both you have to take in the same unit, coulomb meter. Remember this thing. Now if I do multiply it is by 100%, from there you will get the percentage of ionic character of the bond. Now my question is, if dipole moment is given of a particular bond like HCl or HF, and E you know already, bond length is given, from there you will get easily the percentage of ionic character of a bond. What is the important application of dipole moment measurement? And from the dipole moment of a bond, you will get idea about the molecular moment. To get the molecular moment, there you have to know the structure of the molecule and the actual shape of the molecule. Actual shape of the molecule. You know, I told you this dipole moment measurement of a molecule will give idea about the polarity of the molecule as well as dielectric constant of the solvent if it, in its liquid state. Now if I do compare the dipole moment remember not only depends on delta, also depends on bond length. Remember this. Now I will do apply in molecule. If I draw a simple molecule, carbon dioxide. See, carbon dioxide structure shape, you know, this is a linear. And you know, the bond moment direction, always remember from electron deficient to electron rich, that I told you, the dipole moment with respect to the positive electric field. And here the CO bond moment operating opposite direction, and the angle you know perfect 180 degree, and you have idea about the vector, then molecular moment of carbon dioxide will be the zero, since both are equal value and it will be cancelled out. That's why although there are CO bond moment, but the molecular moment of carbon dioxide is zero, and that zero value of dipole moment, it is the experimental measurement will confirm the linear shape of carbon dioxide molecule. Now, I'll give another example, BF3 or BX3. You can take generally any boron trihalides you can apply. I am taking the general BX3. From the concept of hybridization, you know its shape is trigonal planar. This is X, this is X, this is X. And you know angles are perfectly 120 degree. And the direction of bond moment along X, since you know here X is more electronegative than boron. Now you have idea about the vector. If this angle is 120 degree, and if I take the value of this Bx bond moment is mu, then the resultant, consider these two bonds, 180 degree, the resultant moment, you know the formula, root under mu square plus 2 mu into mu cos 120 degree. If you do calculation, then you will get a direction of these two Bx bond moment along this with equal value of mu, which is mu, and it will be linearly 180 degree. This is the resultant of these two, and this is linearly oriented and opposite direction. That's why here also the molecular moment of BX3 you got 0, which will confirm the shape of BX3 molecule is trigonal planar. If I take a tetrahedral, let it is X, it may be H, no problem. X may be anything. It is a symmetrical tetrahedral, you know alternate bonds are oriented along the alternate corner of the cube. And angles are, you know, 109 degree, 28 minute, all angles are 109 degree, 28 minute. If I take these four pairs, you know alternate corner of the cube just like this. This bonds oriented along that corner, this is along that corner, this is along that corner, this is tetrahedral. See, and all angles are 109 degree, 28 minute. Now if I take these two bonds, there you will get resultant vector along this direction. If I take this, you will get resultant vector along this direction, and overall will be the cancelled out if all are X, all are similar. Here also there are CX bond moment, but total dipole moment will get here 0. I am going to give another example like XCF2, xenon fluoride. XCF2, you know the structure is linear. This is linear and lone pairs oriented along the equatorial bonds, and which are mutual angle is 120 degree. This is the trigonal planar part. This 3 lone pair moment will be cancelled out, and this XF bond moment also cancelled out. Since it is perfectly 180 degree, here also you will get mu is equal to 0. But if I take NF3 molecule or NH3 molecule, see NH3 molecule, it is a pyramidal shape. It is a pyramidal shape. Bond moment operates along this direction. This NH bond moment along this direction. This NH bond moment along operates in this direction. And if I take a qualitative idea of resultant NH moment, this will operate along this direction. And this is the overall or resultant NH bond moment. And lone pair, you know electron cloud, and we are measuring the moment with respect to the positive electric field. That's why lone pair moment also operates same direction. The resultant moments you will get very high. The NH3 there will get resultant moment which is very high. This is not equals to 0. And you know water, the common universal solvent we will use. It's the high dielectric constant, water, and you know the shape of water molecule is V shape, angle near about 104.5 degree. 104.5 degree. Then you get 2 lone pairs, and overall lone pair moment operate this direction, OH bond moment in this direction, both will operate along same direction, and resultant molecular moment of water molecule is too much high. And you know water due to hydrogen bonding liquid, and dipole moment is too much high, its dielectric constant value is too much high. That means you got idea from the molecular shape, and you have idea about the bond moment. From there you can predict whether its dipole moment high or low, or it is 0 or non-zero. I will to compare some molecule. I will to compare the comparable molecule, their dipole moment I am going to compare. If I do compare Compare the dipole moment of NF3 and NH3 molecule. Compare these two. Take their structure. You know NF3 molecule structure is pyramidal like ammonia. Lone pair here. And NH3 molecule here, this is the structure, similar structure, comparable species. Now one thing is important here. You know fluorine is more electronegative than nitrogen. Now here the bond moment direction along this. Take resultant in a bond moment. Qualitatively, if I take resultant in a bond moment, this will operates along this direction. Lone pair moment, this, and which will be cancelled out. Since it is not by equal amount, that's why it is not zero. But remember its dipole moment is less. Here see the NH resultant bond moment. NH resultant bond moment. This I am taking the NH resultant bond moment, and lone pair moment operating in same direction along. That's why its resultant moment is high. Its resultant moment is less. The answer NF bond moment and lone pair moment on nitrogen operating opposite direction in NF3 molecule. Since fluorine is more electronegative than nitrogen. However, here in ammonia molecule, the resultant NH bond moment and the lone pair moment operate along the same direction. That's why its dipole moment is high. It is a very common problem, you know. It is a very common problem. Compare the dipole moment of CH3Cl, methylene chloride CH2Cl2, chloroform CHCl3 and CCl4. How do you will compare? See, man, you know the structure of, these are the methane derivative. You know the structure is tetrahedral. Take by this way. Here you know CH bond moment, carbon is more electronegative than hydrogen. The bond moment operates along this direction. Chlorine is more electronegative than carbon. This will operate also in the same direction. The overall moment is high. But if I change one hydrogen by chlorine, that is if I take methylene chloride, then this bond moment reduces and this will operate along this direction. Overall molecular moment decreases due to substitution of hydrogen by chlorine. That's why if I draw the order of dipole moment, it will be the maximum, then reduces, and you know this is zero since it is perfectly tetrahedral and all substituents or atoms are same. Now another example, if I compare the dipole moment, is a very common question. CH3F methyl fluoride, CH3Cl methyl chloride, CH3Br methyl bromide and CH3I methyl iodide. An important example. If I do consider only the charge separation, remember fluorine is most electronegative. Maximum charge separation you will get in fluorine, then the separation of charge decreases due to decrease of electronegativity of the halogen. But you know dipole moment not only depends on charge separation, it will depends on bond length also. Many times I told you in different class that is CF bond is abnormally small in length. Due to fluorine is highly electronegative and is small in size. You know dipole moment is the charge separation into bond length. Due to bond length they will get an exception. Abnormally dipole moment of methyl fluoride slightly less than fluoride slightly less than chloride due to its small bond length, and their rest part is normal order, that is bromide and CH3 iodide. Here you got exception, and this exception due to exceptionally small bond length between carbon and fluorine. Remember this part, very important example. This is called vinyl chloride. You can take X, fluorine or fluorine. I am taking ethyl chloride. Now which dipole moment more? You can explain by taking two concepts. You know this is CH, sorry. This is sp2 hybridized. This is sp3 hybridized. And this carbon is more electropositive than this due to less S character. X electronegativity fixed. Now to consider the difference of electronegativity. Here you will get difference of electronegativity more, since sp3 carbon more electropositive than sp2. So by considering the difference of electronegativity, this bond should more polar than this. I am not considering this part is common, more or less common for both. Now this greater by considering the electronegativity difference, ethyl chloride dipole moment greater than vinyl chloride. Now the question is, another way by you can explain it. You know, if X is halogen, it has lone pair of electron. If I take the canonical or resonating structure concept, a little bit contribution, although the contribution is too much less, it may be 0.001%. You will get another canonical form. See this canonical form. Here you will get CH2 minus, single bond CH, double bond X plus. Although its contribution is too much less, but if you see, if you take this contribution, if you consider the existence of this canonical form, here the direction of dipole moment along this X to carbon. I told you, direction of dipole moment always from electron deficient to electron rich. Although it is 99.9%, here the direction of dipole moment along this. This contribution of vinyl chloride reduces the overall dipole moment of the vinyl chloride. That means you can explain by using both concepts. And similar if I take it cyclic cyclohexyl chloride, here also sp2. And if I take chlorobenzene, similar explanation by taking resonance as well as electronegativity difference, there you will get dipole moment of cyclohexyl chloride greater than chlorobenzene. The same explanation, same concept. I am taking the last example from the organic compound, organic part. You know, if I take 1,2-dichlorobenzene, I will to compare here dipole moment. 1,2-dichlorobenzene. This is 1,2-dichlorobenzene. Orthodichlorobenzene, you can say. This is meta-dichlorobenzene. And the last I am taking, this is para-dichlorobenzene. You know, this angle is 60 degree. Vector. This angle is 120 degree. This angle is 120 degree. And this angle is 180 degree. Very simple thought. Opposite its dipole moment, you will get 0 para. If I consider this is mu, CCl bond moment is mu, this is mu, and take vector mu square plus mu square, root under mu square plus 2 mu into mu cos 60 degree, the resultant vector will operate along this direction, its value is root 3 mu. Take 120 degree cos 120 minus of, you will get resultant vector along this direction mu. That means the dipole moment of ortho greater than meta greater than para, you will get 0 since both are similar. Here, one thing I want to generalize with you. If the two groups are similar in nature with respect to electron withdrawing or donor, both are electron withdrawing or both are donor, for example, then always you will get ortho maximum, para minimum. It may be 0 if they are equal. But when the two groups are opposite in nature, then you will get para maximum, ortho minimum. If time will permit, I'll discuss many more examples. By taking the concept of bond moment and dipole moment, I'll apply the shape of the molecule. You will get idea about the boiling point. Also, you will get idea about the stability. So many examples are there that, if time permit, I'll discuss in the next part of the dipole moment video. So stay with us. Thank you.